My topic was about cybersecurity models and how machine learning could potentially help the growth of cybersecurity models. And also, my name is Aarya, and my mentor was Professor Seta Whitby from the University of La Verne. Um, okay, so first of all, what is cybersecurity? So, cybersecurity is basically a field that protects computer systems and programs from any malicious viruses intended to disrupt and take advantage of data through the hardware or software of the device. And these threats are often produced by gaining access to unauthorized information, seeking vulnerabilities in programs to then take advantage of them, and many other techniques. And these techniques have been growing at a very continuous rate, as you can see with this graph, because as technology advances, these other malicious viruses also advance, and not just the positive aspects of technology. And so because of this, cybersecurity must also grow alongside cyber threats, which makes this field a very important field, and that is why I decided to do research on this. So before we get into the machine learning aspect, um, the evolution of cybersecurity models and what they actually do is very important to understand. And so around 1971, the first virus was invented, and it was mainly invented for a scientific purpose. It was to discover how a program could reach multiple computers, and it was supposed to be non-threatening and just displayed the message, "I'm the creeper, catch me if you can." But this one small information spread to many harmful people intended to take advantage of information, and then this whole cyber threat and all of these threats just started appearing. And because of that, around the late or like a few years after the first virus, encryption was developed by a technology company called IBM to protect its customers' data. And their entire idea is to convert the data that the user wants to protect into a unreadable text or like some sort of code, and only the user can have this access key, but it's a technological access key, not a physical, of course. And the text cannot be deciphered, or the data cannot be deciphered unless you have access to that key. And so that's the whole process of encryption in a nutshell basically. And then in the 1980s, firewall software was developed by Cisco Systems and Digital Equipment Corporation to monitor ongoing network traffic in computers. And how it really does this is each program has a bunch of IP addresses being thrown at them. Basically, when you click on a website, your own IP address goes to that website, and these programs track those IP addresses to see if any address looks weird or suspicious, and it will just block that. And even if you're not suspicious, it might block you if your IP address might seem suspicious. That's kind of rare, but sometimes when you have firewall software, you might experience not being able to continue on to a website because they'll say that the website is suspicious. And that's basically how a firewall software works. And so finally, what is machine learning? So machine learning is a subset of artificial intelligence, and it consists of multiple algorithms aimed at training a computer model to identify trends and correlations within data sets. And the thing is, they actually create the models themselves and like train them themselves. The models don't actually like train themselves basically. And there are two sets of machine learning models. There's a supervised set and an unsupervised set. In a supervised set, the model is given an endpoint and a start point, and the main reason the model is even invented is to create a pattern that leads the start point to the endpoint. However, an unsupervised model only gives the model the data, and the model just has to create the correlation itself and find the endpoints itself. So in a sense, unsupervised is a bit more complicated than supervised, but that's the gist of both of them. And based on the previous information, my approach was to research almost all. There are tons of machine learning models out there, but research most machine learning models and identify two specific supervised and unsupervised learning algorithms and compare them to cybersecurity software to discover any sort of intersectionality, and then see if that intersection could possibly be used later on, and also highlight any limitations of these approaches. So supervised learning, again, it's basically when the programmer gives the model an endpoint and the model just traces down to the endpoint. And one example of the model is a decision tree. And so a decision tree is a model that identifies outcomes from a given data through evaluations within branches of nodes. And basically it starts at a root node, and based on its evaluation, it extends down to internal or decision nodes, and these leaf nodes are the endpoints. So these leaf nodes are what the model is provided with. So it's given a root node and a leaf node, and depending on how big the data is, there are more or less internal or decision nodes, but this is a very simplified version of a decision tree. And a proposed intersection that I found between them is spoofing, which is basically when hackers create a trustable looking website or program that looks to be a good trustable company, and so users will go onto their program and enter their information, and they'll click something on the program. It could be the button, it could be a program, the entire program itself, and it'll just gain most of the user's data. And I thought maybe we could use decision trees to determine ways spoofing can occur by tracking the user's steps while using the specific program to then identify exactly when their information gets taken advantage of. And the specific steps would represent the internal nodes, and the endpoint, or when their information is taken advantage of, would be the leaf nodes. And that would be my approach to decision trees. And another supervised learning model is linear regression. So the main gist of linear regression is it learns from labeled data sets and maps the data points to create a linear model and make predictions on new data sets given. I don't know why I put 2 periods there. Whoops, did not mean for that to happen. Anyways, there are 2 types of regression models. There's a simple regression model. It involves only one independent and dependent variable. It's just like the y equals mx plus b formula, very simple and straightforward. However, there's a multiple regression model as well, and it involves many independent variables. So think of y equals mx plus b, but multiple x's. So the slope is very slanted, and it's like a 3D kind of linear model, if that makes sense. And so there are different ways you could use a simple linear regression and a multiple linear regression in cybersecurity, depending on how many independent variables are impacting the overall thing being researched. So a simple regression model could be tracking the number of phishing cases over a period of time in one platform. And the one platform is very important here, because then it ensures that there is only one x variables. And a multiple linear regression could track total phishing cases over a period of time in multiple platforms. So the multiple platforms would represent the multiple x variables, or independent variables. And finally, unsupervised learning is when the model will arrive at a conclusion of the data given independently without intervention from humans. It will start finding similarities between the data sets and clustering them, or pinpointing the relationship between different points of the data to arrive at its own endpoint, I don't know why the picture isn't showing, but it's okay. So density-based clustering is an algorithm that clusters data points based on the distance between those points and creates a neighborhood of a certain cluster and another neighborhood of a certain cluster to view their relationships. It basically creates a radius value, and based on the radius value, it determines if a certain circle is in relation to another circle. So if it's a neighborhood, surrounding neighborhood. It's a little complicated, but that is the overall main idea of this algorithm. And it's mainly used to determine similarities and overall patterns between data points. So it could help track similarities between different cases of network trafficking. Or it could also track IP addresses from a common site to determine similar categories of IP addresses. So if an IP address doesn't match that similar category or neighborhood, then it's probably not a safe address and it should probably be blocked. And that is the overall idea of using density-based clustering in cybersecurity. Another way we could use unsupervised learning is through a priori. I think it's a priori. I don't know how to pronounce that very well, but a priori associative algorithm. And this is an algorithm that generates frequently occurring item sets in a certain set of data and uses those item sets to create association rules according to its confidence threshold, which is basically the probability that a transaction containing a data type or value X in a rule also contains the data type or value Y. And the equation used to create these rules is if I, which is the independent data, is divided by S and multiplied by 100, it represents the minimum confidence threshold. And this rule just summarizes this entire thing. And so an item or a combination of S items recommends the values remaining when S is subtracted from I. So that was a lot of information, but this table basically summarizes or gives an example of how this is used. So an item and a support value are the two main data sets that create these rules. And so a great way I thought we could utilize this algorithm in cybersecurity is by generating rules of network traffic to better analyze what sources have suspicious patterns and where those patterns generate from, so their root source. And so the item sets can be obtained from network sources, so like IP addresses again, because they're very prevalent in many programs, to then link the given data to its target, which is the source or the program it is entering in, and develop a connection. And this is a very simplified version that, This is a very simplified version that shows how it could be used with simple numbers. So all of these items are just all of the Y variables represented in a different table, and the support just shows how many times it occurs within the data. And then it basically prunes it again to determine if it meets the minimum support. So minimum support is like how many times it should occur within the data for it to be valuable. And so you see how all of these support values are greater than 2, or they're 2 or greater than 2, that it basically goes through the pruning process in order to arrive at a final table data to then go through and create these possible rules. But all of these ideas also have limitations. So decision trees, we will have, in order to track down the user's the users like okay. Can you guys hear me? Just in case.
Yeah, I can hear you. You're good.
Okay. Okay. So some limitations of each algorithm techniques that I just presented would be that for decision trees, we would have to retrieve the code and the user data. So like each step the user took before their data was taken advantage of, and the code during that process when their data was taken advantage of, which can be a pretty challenging task because who knows where their code is located or how to track it. That is the main problem with using decision trees. For density-based spatial clustering, it does not include any outlying data points within the model. I don't know if this doesn't make sense without the picture, but the picture won't show, which is weird. But, oh, whoops. Okay. But any outlying data points within the circle will not be included in the circle. So if the outlying data point represents a suspicious IP address that could potentially be beneficial within the overall data, then it will exclude that. So in order to, it will only identify similarities, it won't add any sort of differences. So we will need to use a different method in order to do that kind of evaluation, and this won't work for that. The data will also have to be converted into a numerical representation because its radius is calculated in a numerical value, so it cannot be inferred. We'll just have to assign some numbers to other values, even if it's like words or non-integer values. And so the numerical representation data values might not be convertible and it might be unsuitable for this algorithm, which can present a challenge. And for linear regression, the pattern being obtained must be presented in a linear way. So in order to determine other patterns that are probably in the shape of a quadratic or an exponential curve, a linear regression will not be suitable for that kind of data. And assessing the data and identifying the important part of the data will also be a challenge because only the important aspects of the data will be included in the linear regression in order to measure its value over time. And so before even including the data into the linear regression model, it'll have to go through a process to determine if the data is even valuable enough to be included in the model. And for associative a priori models, obtaining the sources that access the target source would be a challenge because we can't like access exactly when this virus will occur within the source. And so obtaining that data can be a challenge because the time when the virus infects the program is never fixed. And evaluating the complex rules to determine the significance in the network flow is also another challenge because the rules might also have to be converted into a numerical representation, just like linear regressions and density-based spatial clustering. And so evaluating the rules in terms of its original data instead of its numerical representation can be challenging and can also result in either biases or errors in processing the data, which can be a serious limitation. Okay. So the future of cybersecurity, many advancements can be made to pre-existing or new cybersecurity models using subsets of artificial intelligence, even outside of machine learning. But this research project mainly focuses on machine learning models, but there are also many other artificial intelligence models outside of machine learning that can also be used within cybersecurity. And some challenges is the increasing sophistication of cyber attacks can make it very difficult for those attacks to be traced down and stopped, because as technology advances again, you can never predict exactly when a virus will infect something or how it will infect something. You just have to infer and keep training models and enhancing existing cybersecurity models like firewalls to try to get a best shot at catching the viruses. But hopefully machine learning can assist in advancements throughout time and can be used in the ways or the approaches that I previously stated before. And lastly, thank you, Talaria, for this amazing experience. I've never actually researched cybersecurity before, so this was something completely new to me. And I also want to thank my professor, Seta Whitby, for introducing me into this project and into this field. It really suited my interests, and I might pursue something in cybersecurity moving forward, mainly because of this project. And finally, if there are any questions, comments, concerns, the slide is here. Yeah, thank you.